All right, now that we've got kind of the, well, slow stuff out of the way, it's time to start getting into the meat of this engine. In this video, what we're going to be doing is implementing the bike class, with primary focus being on basic movement and getting the input system working. Now, to have basic movement in place, remember, we've got to get our timing system set up. Remember the old analogy that I used back at the very beginning of this section where I talked about sand traveling through an hourglass? Well, we're going to be setting all of that up in this video here. Now, we're not going to have smooth movement. We're going to get that smooth interpolation taking place at the very end of these videos, so it will be a bit choppy. That is intentional because we are moving from grid block to grid block or cell to cell. So we're going to go ahead and get all the movement in place, and then we're also going to tie in the brakes so that we can use the right trigger on the controller to slow the bike down or even bring the bike to a stop. And finally, there will be no walls in this video. We'll start adding walls into the next video. So if by the end of this video, Logan's able to grab a controller, I grab a controller, and we can drive two different bikes around the screen, I'll be happy. We'll have accomplished everything we set out to do. So Logan, with that, let's go ahead and turn our attention over to the bike class.
All right, moving over to bike. The first thing we need to talk about in bike is the idea of the bike's direction.
Okay.
We have a position that we inherit from Actor, but inside of a bike, we know that the bike can move up, down, left, or right. So we need some way of storing that direction. And what we're going to do is store it in a vector 2. This makes it very convenient because that way we can use a unit vector that is pointing up, down, left, or right to influence the position every time we move the bike.
Okay.
Now, to make this one step easier, we can put all four directions into a struct, and then we can address the directions by name instead of having to remember what components of a vector represent up, down, left, and right.
That sounds good.
So what I'm actually going to do is to begin with a direction struct. So we have our struct called direction. And the struct is going to be made up of four public properties. These properties are going to be vector 2s, and being properties allows us to hard-code in the return result. So let's make the first one. The first property is going to be the direction up. This is going to be a public static vector 2 called up. Inside of the property, we'll give it a get accessor. The get accessor will return the vector, return a new vector, that should point in the up direction based on how a sprite batch works. So that means up is going to have 0 movement in x and -1 in y. Moving negative when drawing using a sprite batch will move the sprite in question up.
That's right.
So we can end off the property. Now, before I make the other properties, I'm going to condense the entire property down to one line. This will, of course, save space when we have 4 of these. So I'm just going to move all of the brackets and different pieces of the line all on the same line. Now I can copy the up property, paste it 3 times, and then change the property to down, left, and right. Down is going to be represented by positive y. Left is going to be represented by -1x and 0y. And right is going to be represented by positive 1x and 0y. So this takes care of all the directions we will need to deal with when moving bikes around.
Okay, so now we can go ahead and turn our attention over to the actual class where we will begin with our fields.
All right, and the first 2 fields are going to be direction and desired direction. Let me drop them down and I'll explain why there's 2 different direction fields. Both of these fields will be private and of type vector 2. The first will simply be direction, and the second, vector 2, will be desired direction.
Now, before you explain these, Logan, sometimes I get ahead with my thoughts. Did you explain why you put each of those properties as static up in the struct?
Actually, I have not yet. The reason I had done that is if I had not made them static, we would need an instance of that struct.
That's right.
And instead, I would rather have this as a template where we just look back to direction.
So it just serves as a lookup, basically.
Exactly. Or rather, we can look it up by just saying direction dot some direction.
Precisely.
As opposed to
direction dot up and boom, there you go.
Exactly. Instead of having to make an actual direction, which just wouldn't make sense then.
Right. I just wanted to make sure everybody knew that.
Right. It just makes a very easy lookup table.
Now, we have direction and desired direction. So we have these 2 different fields for direction. Why?
The reason for this is because there is an amount of time which passes before the bike actually moves. Direction is only going to be considered as the bike is moving from one grid block to another grid block, and at no other time. Now that means that time is going to pass while the block is essentially sitting still before it moves to another position. And what would happen is if the user was to push any direction on the D-pad, during that time, that input would get lost because they would be pressing a direction. If they weren't pressing it while the time ran out to move the block, the direction would simply be thrown out, not considered.
That's right, because if they let go of it, then, well, that particular direction is no longer in play at that given slice of time.
Right. So what desired direction does is acts as an input buffer. Desired direction is allowed to be set at any time, whether the bike is currently moving a grid space or not. So what that does is if let's say the bike is moving in the up direction, and let's say the right direction is pressed very briefly and then released on the D-pad. What that does is it immediately sets desired direction, but then waits until the bike moves. When the bike moves, it looks at direction, moves by that direction, and then takes the desired direction into account. So that way, no matter how much time has passed since the direction has been released until the actual move, it still gets considered instead of being dropped.
Absolutely. Also, it's very handy in a couple of other cases as well. One being that you can use it to check to make sure that the player is not trying to double back on themselves, like do a 180 right back into their wall. That wouldn't be good. And also, we can use that in direction in determining if we've just turned to the right, to the left, or whatever, so that we can determine which corner piece we need to use.
Right, looking at any possible differences between the two can tell us what our last direction is versus what our new direction is going to be, and from that difference decide what kind of grid block to draw. Do we draw a straight line, a horizontal line, a vertical line, or a corner line?
Exactly.
And, all right, well, now we can move on to another field, and that is the player index field. This field will be public, because we need to access it when gathering input. And this will be the player index field. So it will be of type player index, and it will be called player index.
All right, so now what we're going to do is go ahead and set up the fields for our timing system that we talked about. Remember, once again, when we had the hourglass, we put that sand in there. We said that sand was more or less considered, the amount of sand left was the time remaining. And then the move interval, you was able to look at that as kind of how much sand we had in there, how much time to chip away at. So we'll go ahead and set these fields up now. Got two fields and a property.
All right. The reasoning here is that both fields are going to be private, and the property is going to allow access to move interval. And it is a property because we need to take time remaining into account when we set it. But I'll leave that for the property itself. First, we have the two private fields. The first is a private double for time remaining, and another private double for move interval. All right, now we're going to create the public property, so public double move interval, and we'll fix the spelling on double. The reason this is a property is when move interval is set, we need to make sure that the time remaining, the sand left that's ticking down, is not somehow larger than move interval. Because we have an adjustable move interval. They have the trigger that acts as a brake. Applying the brake increases the move interval. We want to make sure that that effect doesn't have to wear off on its own, which would mean we would release the brake and see a visible lag before the bike would speed up again. Instead, we want to make sure that if the move interval decreases, that the time remaining is no greater than move interval.
Right.
So what we'll do is we'll break this up. We have our get accessor, and get is still going to be very simple. It'll just tell what the move interval is. So it will simply return this dot move interval. The set accessor is where we need to make sure that the time remaining is less than or is equal to or less than the move interval. So we'll perform a check and make sure that this dot time remaining is greater than, or excuse me, if it's greater than this dot move interval, then we need to cap it back down, because if time, and this is important to check like this, because if time remaining is less than, we don't want to override it because it might be counting down to some getting ready to move.
Exactly.
But if it's over, what that could mean is we had just been braking and then suddenly released the brake. Now we need to make sure we just lop off that extra time and make sure that it's exactly set to the move interval.
It's our way of pulling some sand back out.
Exactly. So time remaining is going to be equal to this dot move interval. And that will take care of the move interval property and also takes care of all of the fields for the bike class.
All right, with all the fields out of the way, let's go ahead and skeleton in the rest of our methods here so that, as we start implementing them, they are able to call upon one another. You can build without any problems, etc.
Exactly. And we're going to begin with the public constructor. The constructor for bike is going to need to take in 3 parameters. We're going to need to take in a player index, a position, and a direction. So the player index is going to be of type player index and called player index. The position is going to be a vector 2, and the direction is also going to be a vector 2. Alright, the next method is going to be an override to the update method from actor. So we'll make a public override for update, and we will remove the call to base since we know that it does nothing.
That's right.
The next method is the draw method, which is also an override to actor. So we override draw and remove the call to base. The next method is the move method. This is a private method which is going to handle using the direction to influence position or to increment position. And this is going to be, again, the move method. And after move, we have change direction. And this is going to be a public method that allows external influence on the bike itself, telling it to now take a new direction. So change direction is going to need to take in a vector 2 as the desired direction. All right.
All right, very good. So now that we've got the skeletoning done, it's time to start some implementation. Let's go ahead and start out by implementing our constructor first.
All right, inside the constructor, the first thing to do is to take all of the data given as parameters and account for that in fields. So beginning with the player index, we'll set this dot player index to the given player index parameter. Then we'll look at the position, set our position to the given position. Then we'll set our direction to the given direction. We'll also set the desired direction to be equal to the given direction. Since desired direction, we don't want to have that somehow be different than direction as we begin moving. Otherwise, we could have an inaccurate graphic being drawn or even inaccurate direction being used. So those are all the fields that we can gather from the parameters. The other 2 fields are going to be filled using information back in game 1. The first piece of information is going to be the move interval. We'll initialize...
I was just going to say, basically now we need that amount of sand, and we're going to get that from game 1 where we had the bike move interval, and then we had set that up as 0.05.
Back in game.
That's right.
So that takes care of move interval, and one last thing is the bike's origin. So we'll set our origin equal to game1 dot bike origin.
Okay, and that gets the bike set up. So from here, let's go ahead and move on down to update.
All right, inside of update, this is the method that treats time remaining and move interval as an imaginary hourglass. This is where we need to take time away from time remaining and then see if that has crossed 0 if we've run out of time.
So basically, this is our timing system. This is the heart of the timing system.
There is one other thing that update is going to be responsible for, and that is going to be respecting the bike stop threshold. Because once the bike stop, or once the speed goes above the threshold, we want to make sure we stop moving the bike. Move is going to be driven by update. So it's inside of update that we'll check and see if we should be stopped or not. Because if we're stopped, we're going to stop counting time down.
That's
so that way if we were to start again, we have the appropriate time left before another move.
Exactly.
So the very first check is going to be if we should be stopped. And that check is going to be done by looking at the move interval and making sure that that is less than the bike stop threshold. So a low value move interval means moving faster. So this means is the move interval moving faster than the bike stop threshold? If it is, then we need to count down time until time hits 0.
Yeah, that basically the system needs to keep running.
Exactly.
Sand can keep falling out, etc.
Right, and that means to take time remaining and decrement it by the amount of time that has gone by. That's found in gametime.elapsed game time, which we'll read as total seconds. Now we need to check and see if that time remaining has just crossed 0. So we'll look at the time remaining and see if it is less than or equal to 0. If that's the case, then we've crossed the point at which we need to perform a move. So we'll call the move method. We'll also reset the time remaining so that another interval can begin counting. So this dot time remaining will be set to the move interval. And that takes care of the update method.
Okay. So with update out of the way, let's go ahead and turn our attention over to draw.
All right, inside of draw. Draw needs to translate the unit-by-unit positions that are found in the position field and translate that into an actual position on screen. Because moving the bike one grid block, so that would be moving position by 1, actually needs to cause it to visually move 8 pixels, 8 being the size of the grid block size back in game 1. So to store this offset, what I'm going to do is make a vector2 called draw position. So we have visual position versus actual grid position held internally. And draw position is going to be initialized to the current position times the grid block size. So fill in grid block size, and that way we'll move by blocks of 8 instead of by 1 as positions updated.
Exactly.
All right, the next thing we need to do is we need to get the rotation for the graphic. Since the graphic by default is simply pointing up, we'll use the sprite batch's rotation functionality to point it in the desired direction. And in the breakout game, we saw how to use a vector2 to gain a rotation angle in radians using the A102 method. So we'll store that in a rotation value we can feed to the sprite batch. So I'll make a float called rotation. We'll set that rotation equal to the float casted result of math.A102. And we need to feed y and x to A102. So we're going to take in the directions y, so this dot direction dot y and this dot direction dot x. I'm going to end off the statement here, but keep in mind that there's going to be a small problem with this direction. We'll need
small problem. A big direction. It's just not going to be
very
pointing the right
minor
way.
offset that'll need to be added, probably on the order of about 90 degrees.
That sounds about right. So that when we first show the bike drawn here in just a minute, and you see it moving,
it's only going to be pointing in entirely the wrong direction.
Yeah, it just might not be pointing in the right direction, and we know that. Okay, so we'll be coming back to this area right here, but moving right along.
All right, one other piece of information we need to gather before we draw is what color to draw the tail graphic as. We know that back in Game 1 we have that player colors array, which has 2 colors in it for player 1 and 2, but we need to decide what color to use because we're in the code here in any instance of bike. Well, we know which bike we're supposed to be by the player index. But player index is an enumeration, not a number we can directly use in the array. But let's look at the player index briefly. Let's go up to player index back where we had defined the field. Let's right-click on it and go to its definition. And then, of course, we can see player index and the familiar words 1, 2, 3, and 4. But we can see that those values, or those fields, are set to the numerical values 0, 1, 2, and 3. This nicely represents the range that an array could cover, which we have back in Game 1 as our player colors, which means if we were to cast a player index, we could use that casted integer inside of the color array to gain access to element 0 or 1, or even more if we had more players. So back in bike, what I want to do is cast our player index over to an integer and use that to reference a color. So let me make that color variable. That's going to be called the tail color, and we need to set that to game1 dot player colors, and then we need some integer in order to address the an element in the array, and that is going to be this dot player index. Now, of course, we need to cast that in order to feed it to the array, so we'll cast it to an integer. If we do that, we should be able to resolve the player index over to a color. And now we have enough information to perform the actual draw.
So we've got, of course, 2 things to draw, as we talked about at the very beginning here. We mentioned that the bike was made up of 2 different graphics. So we've got the tail and the body itself.
So let's start with the bike, the body of the bike. Let's make a call to spritebatch.draw, and let's look at the 6th overload. The first thing, of course, that we need is the texture. So we'll grab Game 1's bike texture. We're going to draw it at the position given in draw position. We're not going to have any source rectangle. The color is going to be white. As we discussed earlier, the bike body itself does not take on the color of the trail. The rotation we have found and stored in the rotation variable. The origin is stored in the origin field for the current bike. The scale will be a value of 1. Sprite effects will be none. And layer depth will be 0. Now we need to draw the tail of the bike. And to do that, I'm going to copy the first draw line and paste that in below. And let me erase that backslash. Now only two things need to be changed. Of course, the texture itself needs to be changed. Instead, we'll draw the tail texture. And the color needs to use the tail color. And that should be all we need for the draw method.
Very cool.
Now we can move on to the move method. And move is, for the time being, going to be very simplistic. We're only going to do two things. We're going to advance the position by the current direction. Then we're going to turn around and update the direction to be set to whatever the desired direction is, because the desired direction is a buffer that is to be used only when a move occurs, and to simply wait and remember until that happens. This is where we acknowledge the new desired direction and make sure that our current direction lines up with that. And that's all we're going to have in move for the time being, so we can turn our attention to change direction.
Okay.
Inside of change direction, the only thing we're actually doing here is setting the desired direction. That would be this desired direction set to the given parameter desired direction. But we want to do a check before we assign this. We want to make sure that the player isn't trying to reverse on themselves, trying to turn 180 degrees, meaning if they were going up, don't allow the player to go down. If they're going right, don't allow them to go left. And that's where the direction being set as a vector is very convenient. What we can do is to do a check and see if the desired vector reversed isn't equal to our current direction. So we can say if the given desired direction parameter is not equal to our current direction times -1. Because the current direction times -1, that would be like saying if direction is up, times -1 would be down.
Yeah.
So make sure that we're not setting one of those reverse directions. If that's the case, then go ahead and acknowledge the desired direction as what we're trying to input.
Okay. All right, so now that we've got this, let's go ahead and build, make sure that nothing explodes. Very nice. Now, with the bike class pretty much wrapped up for the moment, let's go ahead and turn our attention over to the game class.
All right, inside the game class, well, first, let's make a bike. Let's set player 1 to an actual instance of a bike. So here in create scene, we'll set player 1 equal to new bike, and we'll feed this a player index of 1. A position, let's space this, or position this on the left side of the screen, but offset about 10 grid spaces from the top. So let's make a new vector 2, where in X we'll have a position of 0, and in Y let's space 10 grid units off the top, so 10. And let's set the direction to be moving in the right direction. So we'll look at the direction struct and access right. This is where that direction struct becomes very handy. Again, we don't have to decide what components would equal right. We can just look at the direction struct. So let's see. Now if we build, all of the actor infrastructure is already in place, so we should be able to build and run, and we see a moving bike.
That's pointed in the wrong direction.
And pointed entirely in the wrong direction. We have a bike that is moving to the right, but is pointing up.
And not controllable because we don't have input control in yet.
But we'll get to that in just a second after we correct the drawing. Let's go back to bike briefly and go back to the draw method. Looking at it, we see that we need to rotate the bike 90 degrees clockwise. Or in radians, we need to add half pi.
Right.
So we'll grab where we're setting the rotation and offset that by math helper dot pi divided by 2.
Told you it would be messed up.
But now we're pointing in the right direction for the direction we're moving.
All right, let's go ahead and add in a second bike. Position it down at the bottom. Maybe pull it 10 grid unit up. Units up.
I got you.
Wow.
But let's go back to game. Let's go to create scene, and let me duplicate the player 1 line, change the variable to player 2, change the player index to player index dot 2. Now we want this bike to be positioned on the opposite side and corner of the screen. That means we'd rather have it on the right side, and the far right side of the grid is going to be whatever is held in grid width. So all the way over on the right-hand side of the screen. And then we want that to be moved 10 grid units off the bottom of the screen instead of the top. So we'll look at grid height and subtract 10 units.
Sounds good.
And we'll set the initial direction to a direction of left instead of right. Now, if we build and test...
You have no input control?
We have absolutely no input control, so reaching for the controller was entirely futile.
No, it wasn't. It was very entertaining for me. But I'm glad you did that because that takes us to the next thing. Let's go ahead and get some input control into place.
All right, to do that, let's go down to Update. And it's inside of the game's update that will look for input for the different controllers. Now, before I get into the individual game states, I'm going to define a game state variable outside of the entire switch statement. The reason for this is after when we get to using the stop state, I want to use that same variable to gather input. So we'll actually define it outside, and then we can use it in both locations. So I'll make a gamepad state variable called gamepad state. Then inside of the playing state, inside of the actor update loop, what I'll do is jump down and I'll make a bike variable. And then we'll set that bike variable equal to the current actor casted as a bike. And I can, for some reason, suddenly not type the word bike.
I think you're just hungry. You keep typing bake. I'll take a cake, please.
So the next logical progression is cake. And
exactly. There is no cake.
But we'll cast actor as bike. If the cast was successful, then bike will be set to something other than null. So if bike was not equal to null, then we know we are in fact looking at a bike actor and can use that bike to find an appropriate gamepad to pull input from. So we can take our gamepad state variable, set that equal to gamepad.getState. GetState needs a player index, which is held in the current bike. We can look at bike.playerIndex, and that will give us the correct gamepad to use.
And see how nice Logan's being by putting all this if bike's not equal to null. I mean, what all does the actors list contain right now?
2 bikes.
Bikes. but if you guys get...
Again, this is just a little bit of future-proofing. Exactly. If we start adding different kinds of actors, we don't suddenly try to...
Power-ups, etc. You got it. It's already in place.
Exactly. But now that we have a gamepad state, let's look at the D-pad and decide if up, down, left, or right are pressed. So looking at gamepad state, let's look at the D-pad and see if the up value is set to button state.pressed. If it is, then the up direction is pressed, and we need to tell the bike to change its direction to up. So we'll take the current bike, tell it to change direction, giving it the up direction. And again, the direction struct becomes very useful. And with that in place, we can copy the if statement, paste it 3 additional times, and change it all of the directions to their appropriate things like down, left, and right. So dpad.down, dpad.left, and dpad.right. But of course, we need to remember to set the direction itself to down, left, or right. Come on, copy paste. I know you want to.
Oh, and copy paste decided to.
Copy.
Oh, isn't that so nice?
Paste.
When Windows does that.
And well, I misspelled left anyway, so I mean, maybe it's good that I scrutinize this just a little bit more.
I was just holding things up until you caught that. It's advanced.
Amazingly so. A little bit afraid, actually. One other thing I want to do is change the rest of the ifs, ifs to else ifs.
Yeah.
Because you'd have to be really good to press left and right on a D-pad at the same time. All right, that has gamepad input. It is per bike, so let's build and test.
All right, and let's try doubling back, and I cannot.
Nope, if I move down, cannot press up. Ooh. If I move right, cannot press left. I move left, cannot press right. So
at this point, we shall name this game Advanced Robot Termites. Termites. Haha. I was thinking of a movie. Hey, get off me. Termites. We shall call it Robotic Termites.
Also note that the bikes can indeed go off screen.
I'm lost.
We're not doing any kind of collision checking yet.
Okay, I'm really lost now.
So I guess I win then.
I guess so, because I don't know. I'm somewhere in memory and just quickly changing locations. Okay, well, so yeah, that was nice. Also, we don't have any braking abilities yet, so.
Right, and that would be the next thing to add, because while we're doing input, let's take a look at the right trigger and make the or implement the brake.
Okay.
Now, thinking about this for a second, we're going to be looking at the right trigger. So if I drop that down briefly, let me see if this works. If we look at gamepad state, look at the triggers. Come on, triggers dot right. And triggers dot right is a float. The range of the trigger is given in a value or a range of 0 to 1.
Mm-hmm.
Now, that's not the most appropriate range for what we're trying to accomplish. If we look back up at the speeds that we are going to be dealing with, we have a move interval of 0.05. That is going to be the fastest speed the bike can move. We have a stop threshold of 0.02, which is the slowest we can move before we stop. So really, that's our desired ranges from 0.2 to 0.05. So what we can do is we can look at both of these values and come up with our own range, and then multiply that against the trigger to get an actual usable range. So what I can do is jump down and add a variable. I'll add a double called speed range. And we'll set that to...
I think we're starting to lose just a little bit of keyboard here.
I think so too. I think the
batteries might be going just a little downhill.
But speed range should be equal to our, what is it, bike move, or bike stop threshold minus our bike move interval. That should give us our working range that we want.
Mm-hmm.
So that value is going to be multiplied against the trigger. So we'd have something like gamepad.triggers.right times the speed range. But then we need to offset by move interval, because simply multiplying this means that if we had no right trigger, or a trigger.right value of 0 times speed range would still be 0. We want the lowest possible value to be bike move interval. So we need to make sure we offset by bike move interval.
Right.
And this whole thing gives us...
And well, let's store that also into...
Exactly. That whole thing gives us the value we need. That value needs to be stored in the bike's move interval.
Yeah.
So we need to take bike.move interval and set that to the value we have come up with from the triggers times speed range plus bike move interval.
So run over that with some examples real quick. If the trigger's not pushed in, you got 0. 0 times speed range is 0
right.
plus, and then there we are with our maximum speed of 0.05 from the bike move interval.
Exactly. 0 times 0 is 0 plus bike move interval would be 0.05, or the fastest speed. If we had the trigger pressed all the way in, we would have a trigger.right value of 1. 1 times speed range would be whatever 0.2 minus 0.015 is. I guess 0.15. Who knows? It's
too much math for me.
We're doing logic and not math, so it doesn't matter. We're doing the appropriate range multiplied by speed range. Again,
plus that's the number gets bigger.
Right, exactly.
Which means the bike gets slower.
Exactly. I like your math. You have good math.
All right, very cool.
So now we should be able to test.
Yes. And oh, I think something might not be working right.
Indeed.
But I found myself. I came back on. That's kind of cool.
All right, let's look at what we're doing. Maybe we're subtracting the wrong thing from the other thing.
We kind of got ahead of ourselves. We left out one little important piece of code as we were explaining things. Logan?
Well, if we look back over in the bike class, we left out the setting of the move interval field. We have the move interval property. That's what we're working with back in the game class. We're looking at the time remaining, but we seem to have omitted the move interval field itself. It never gets set.
That's right.
So we need to go in here and set the move interval field equal to the value as well.
That's right.
Before we go on and do the additional check. That way, as we update move interval, we get the actual value recorded. So
now let's give it a try.
Let's build and test. And check it out. Now we have working brakes. Very nice.
Very slow. That's more than slow. That's stop.
And even though it might be a little bit hard to see at 10 frames a second, as we slow down, eventually we get slow enough where it may become apparent that the bike is moving block by block instead of pixel by pixel, because we can start moving very slow, but we still have to move an entire grid block at a time. So
it's a contest. Who can get the closest to the wall and stop? Right there. Oh, yeah. Look at that. That's like 2 pixels off. Disqualified. Okay, very cool. All right. So, well, wait a minute. That's pretty much it.
That's what we set out
we
to do.
have
We've got
accomplished our objectives. Yeah, we've got bikes that we can control moving around the screen. They're a little blocky looking right now, but we do have the ability to slow them down and even bring them to a stop. And that's pretty much it. So yeah, it's going to be the next video where we'll start getting our wall class all flushed out and build just a quick demo wall as kind of a proof of concept that the system does work. And then the final video, we'll get it all tied in. So with that, that is going to wrap up this video. Thanks a lot.